Thank you. I would like to start by thanking the organizers to allow us to contribute also to this workshop, and also to thank you all for having the patience to be here, although temptations outside with the lunch, and I guess everybody's hungry by now. So my talk is a complementary talk to the first talk of the day of Professor Milton about the question of characterizing the response functions or the Dirichlet to Newman maps associated with two-dimensional springs and masses elastic networks. And our work, as you saw in the morning, is in the context of linear elasticity. So a little bit shifted, but it's part of the adventure, I guess, with some of the talks. We've seen some previously, so I'll try to make up for this. This is an example of 7 terminals elastic network. So we are interested in finding the Dirichlet to Newman map at the terminals regardless of the interior nodes. I represented the interior nodes here with the white circles. What is the Dirichlet to Newman maps? In our discussion is what kind of forces correspond to imposed displacement at the nodes, and what are all possible such maps for two-dimensional elastic networks. Here is a definition of the response matrix of an elastic networks with n terminals, x1, x2, xn. So the response matrix is defined as a map from displacement to forces at the terminals. Okay. The title is missing. This is the response matrix for two-terminal spring. Is the simplest Hooke's law for displacement in 2 dimensions. The forces are given at the two ends of the spring, x1 and x2, 2 forces equal opposite size, and is displacement multiplied by the elasticity constant on the direction of the spring vector. In matrix form, as you saw in the morning, Professor Milton showed in his introduction, you can write the law of motion in matrix form, where the stiffness matrix in this case is given by this, n being the Versor vector of the direction between the spring terminals. Now you can extrapolate this in general for a network with no interior nodes, only terminal. Then the static elasticity response matrix is given by the stiffness matrix, which is a block matrix accounting for all the elasticity stiffnesses matrices between the springs. So this is just a simple elasticity theory. When the network has internal nodes, then the Schur complement will come into place. So first, I'll discuss a little bit about elastic energy stored in the network. So if you have a network with I internal nodes and B boundary nodes, these are the index notations for the internal and boundary nodes. Then you can look at the network. One way to understand the response matrix at the terminals is through the energy as a minimization principle. That is, look at the network as all the nodes are terminals. The matrix will be A, interactions given by this, it's a block matrix where ABB accounts for interactions between boundary nodes, ABI interaction with boundary nodes and interior nodes, and AII is accounting for interactions in the interior nodes. And you have that the total elastic energy is related to this quadratic form. For any matrix, such matrix A, again A accounts for all the nodes, boundary and interior. In order to obtain, this is the explicit form of the quadratic function, a quadratic energy functional for the spring, one spring. So the next step, once you have the energy of the network when all the nodes are terminals, the next step is to formulate the minimization principle in order to find out the response matrix at the terminals. So that is the only thing you are free to touch are the terminals, and whatever input you put there, you measure the output. That will give you a relation which we call response matrix, and you can view indirectly, you can view this response matrix W at the terminals as the minimum possible value of the energy when all the nodes are terminals. So you minimize on all possible interior nodes, interior displacements, and you get the energy at the terminals. And this map, this quadratic functional can give the response matrix W at the terminals. And if you do a little bit of computations, the first order optimality conditions for the minimum here would imply here that W is the Schur complement, which is not visible. Now it's not a non-essential thing, so yeah, I guess yeah, if I press escape, I guess I escape. And what do I do now? Oh, just leave it like that. Yeah. Thank you. That's a simple solution to a complex problem within 15 minutes talk. So thank you. You make my day. Okay, so the response matrix W can be taken out, computed from this minimization principle, again by the first order optimality condition, and you get W, which is, again, W is the response matrix or the Dirichlet-Neumann map, displacement to forces. It's called many things in many contexts, and can be viewed also as the Schur complement of the matrix A, given like this when the matrix accounting for internal interactions is invertible. If it's not, then you use the pseudo inverse. So this is what we have for the response matrix characterization in the static two-dimensional elastic networks, and out of those properties we can state necessary conditions for a matrix to be a response matrix. And reciprocity accounts for symmetry. The positive definiteness accounts for the fact that the system does not produce energy, and also in order to avoid rigid motions, the matrix should be balanced. It turns out that these conditions are also sufficient for a matrix to be a response matrix. That is, any matrix satisfying this condition is achievable by a network of springs and masses. Achievable in the sense that you can build a network having its Dirichlet-Neumann map given by this matrix, any matrix satisfying these properties. So this is the theorem we have. One of the theorems we have in our recent paper regarding this is in the context of 2D elasticity, and it says that any matrix which is symmetric, balanced, and positive definite is attainable, can be a Dirichlet-Neumann map for an elastic network. And the way you show this, just a few. Could you please let me know when I have only 3 minutes more? Yeah, 3 minutes is a threshold. Okay, so the way you show this is to spectral decomposition first. You observe that with the spectral decomposition, you can write your matrix as a sum of rank 1 matrices. So the only thing you should be able to do is to focus on rank 1 matrices and show that any rank 1 matrix which is positive definite, symmetric, and balanced can be attained. And once you show this for rank 1 matrices, then the superposition principle tells you that if you have two response maps for a network with the same terminals, then the response the response function of the two networks altogether, when you consider the two networks as one, is the sum of the response functions of the network. So this is a superposition. So that's why if you do it for WIs, for any rank 1 response matrix, then you can do it for their sum. So that's how you build a network to achieve any matrix W. So the first step is decompose, focused on rank 1 matrices. Second step, you show that you can construct a rank 1 network that is a network with a rank 1 matrix for any m terminals having the force proportional to any n tuple of forces in our particular case of this form. So again, UB are the displacements you started initially with, and if you can do that, then the problem would be solved for W. How do you construct a network to mimic a network to have a response proportional to any given set of balanced forces? And we do this in steps. The first, we start with a three-terminal network, and this is kind of, you can build up on previous work in the literature, show this. The open question, though, was for four-terminal networks. How do you show that there is a four-terminal network within the plane to achieve any system of four forces, balanced system of four forces? And if you do that, then you can employ an induction argument for terminals, for more than four terminals, and complete the argument. So just the idea for the proof in the four-terminal networks case is this was the open problem in the static question, and you do this in two steps, sort of. The main step is a very technical property to show that for a given system of four balanced forces, that is, their sum is 0, the sum of torques is 0, you can find a point y star located within a neighborhood, a small neighborhood of the convex hull of the terminals. That is, you don't want to have that point at infinity. So located in a neighborhood of your network, such that you consider this point as an internal node, and you have that there exists a force and a pair of terminals and a force given by Fi plus Fj, such that these triplets are balanced system of forces. Now, once you're able to do this, you proceed with the rest of the proof. The remaining part of the proof is this is how we did, and how one will do the proofs in this context. That is, you're trying to build a network achieving force response proportional to something you want. In our case, F0, F1, F2, F3. I know that because these are balanced system of forces, the first triplet and the second triplet are balanced, then looking at the three-terminal case, which we proved previously, we have that they admit a rank 1 network achieving forces proportional to their forces. Then there are two rank 1 networks achieving the actual responses. Their energy, Q1 and Q2, is given like that, because the matrix, the response matrix, will be proportional to the triplet of forces. Now, what do you do next? You superimpose these networks, and you consider the energy of the resulting sum of the networks as a network, and you use the minimization principle on the internal nodes, so internal displacement. You know that the energy of the sum of the networks will be the minimum of the two energies when the minimum is taken over all possible displacements at y star. Yeah? And the optimality condition here, the first order optimality condition, would imply this relation between FV and the known displacement and forces, and this in turn will give, when plugged in again in the expression for Q, will give the result that indeed you can build a network for any system or balanced system of forces F0, F1, F2, F3. You can build a network with response proportional to those forces. So this is the proof in the 4-terminal case together with a 3-terminal case, and an induction argument will show, would imply the result. Now, the last slide I have is with conclusions and open questions. And now, as Professor Milton suggested earlier, it is amazing, and there was a question about what do we mean by approximation. So I have one. Okay. There is one important result by Kameredin and Seprichet showing that any elastic material can be approximated with isotropic materials. And this approximation is in the sense of Moscow convergence, which is more in plain English words. It says that it's an approximation in the sense of energy, strain, and displacement, but not stress. So it's an approximation in the sense of energy, strain, and displacement. Now, it's amazing that you can view any elastic material like an isotropic material, but even more, our results suggest that you can achieve any linear elastic material. You can approximate it in this sense with springs and masses. It's a discrete network of springs and masses. Now, as Professor Milton pointed out, there are results in the dynamic context. So when you have a certain frequency of motion, there are results suggesting negative mass and exotic properties. Now, can we hope, when passing to the limit from discrete to continuum by using gamma convergence or any other tools, in some sense, when passing to the limit, can we hope to achieve exotic behaviors outside the classical physics that will give us a path towards metamaterials, which we've seen exhibit impressive properties and very hard to understand at the continuum level. So discrete recipes for metamaterial response would be desirable or interesting to look at. So this is what I conclude with. Thank you.